Hello, and welcome to a chemistry class that is all about pH, what that is and how we find it, and what the pH is of several common household ingredients.
So P and H are letters of the alphabet. I know that much.
They are, but pH is so much more than that. Special welcome to you if you are joining us live. We want to give a quick shout out to Caitlin from Bakersfield, California.
Abigail from Virginia, Manny from Michigan, Haley and Noah are from Montana, Amaya watching from the UK.
And a special shout out to Ryder Mark from Boise, Idaho, who turns 8 years old today. Happy birthday, Ryder.
Congratulations.
Hello to Anya watching from Wisconsin, to Winston from Australia, where it's very early in the morning, Lucas from Connecticut, Tegan from New York, and Xander and Quinn from Texas. Happy to have you guys with us here this morning.
Seeing Ryan from Ottawa in the chat. Sydney from Alaska. People all over. We're getting excited here because pH. Are we talking about like
acids and bases? That's what pH is. So to understand pH, the first thing you need to know is that we care a lot about water because we are mostly water. Really, when you think about it, 70% of your body is water. You are a bag of water with a skeleton and muscles for support, but most of you is water. And that's kind of a remarkable.
Actually, there was a Star Trek episode where they encountered this weird alien. They didn't even think it was life, they managed to communicate it with.
It's like
it calls them ugly bags of mostly water.
So the ugly is subjective, but the bag of mostly water is actually fairly factual description for most life that we know of. And we care about water because that's what makes up most of us and most of the ocean and the world around us. Well, water is, as you know, H2O, 2 hydrogen, oxygen. And when you have pure water, some of that water will actually split apart and form 2 ions. So I want you to tell me right now, and if you're watching the replay, you can just say it out loud, which ion is positive and which ion is going to be negative. Because when they split, the oxygen was greedy and the oxygen kept the electron that was being shared in this bond.
So this one has an extra electron, and that one's missing an electron. And you're saying that one of these will be positively charged.
One of these will be positive.
This one
will be negative. Okay, which one is positive?
Which one is the positively charged particle here?
Just go ahead and say it out loud if you're watching the replay or if you're watching live. And the answer is hydrogen. Hydrogen is positive. And this oxygen and hydrogen together, this we call a hydroxide, and it's negative. So in pure water, you have just a couple of these and a couple of these, but you have equal amounts because they came from water. The water itself split apart. And if you have equal amounts, then we call that a neutral pH. Are equal amounts of this safe, Math Dad?
To have equal amounts? Yeah, isn't that what you just said? Water?
Yeah, pure water with very, very small amounts of this, but the amounts are equal. That's really safe. That's pH 7. Now, we can do something pretty awesome if we take pure water and mix it with this. What do you think this is? This is just a piece of a vegetable, and that vegetable is purple cabbage. I took the rest of this purple cabbage and I boiled it with distilled water to make a pH indicator. That means that this purple cabbage juice is going to change color if the pH changes.
Okay, this is sounding like it might be kind of cool. I like color changing, although if you're going to make me eat that cabbage, I don't think it's so cool.
Math Dad does not like cabbage. Don't worry, Math Dad. I will eat the cabbage because I like cabbage.
Well, last time you fed me chocolate, and yeah, we've had a good trend of feeding me, but I don't know if I want that trend to continue today.
No, we're not eating anything today.
Okay, so you said pH of 7. So the low end of the pH scale.
If the numbers go smaller, we're going to get acidic. If the numbers go bigger than 7, we're going to be the opposite of acidic, which is basic. But we'll talk about that in a minute. But first, I want to do our demonstration.
Okay.
So we are going to put on gloves because we've got some chemicals here and safety goggles.
Oh, gotta be ready for this. It's not going to be dangerous. Are we going to make a mess, Science Mom?
We're not going to make a mess today. I don't think so. And we're not going to make anything explode, but we are going to see some awesome color changes. So first, this biggest one right here, I'm going to put just cabbage juice.
So the chat is letting me know that cabbage is delicious.
Cabbage is delicious, Matt
So-
said. Got to
so
get
that
on board here.
Well, I'm okay with cabbage, but I'm not exactly drooling out of anticipation at the idea of eating raw cabbage.
This is a little bit dark, so I'm going to add some more distilled water just to make it a little bit easier for you to see. So
Okay.
that's a really pretty purple color that we have here.
Agreed.
And now we are going to test some different materials and see if they are pink, which is going to be acidic, or green or blue, which means basic. So the first one we're going to test here is vinegar.
Oh.
Wow.
Okay, that got really pink really fast.
The vinegar is super pink. This
Wait,
next
wait, wait.
one,
What did that mean? What did it mean that it turned pink?
everyone say acid.
Acid.
If
Okay.
it turns pink, it's an acid. If it turns blue or green, it's the opposite of an acid, which means basic, or sometimes we call that alkaline. Now,
Okay.
baking soda.
All right, baking soda.
Whoa.
That's definitely bluish.
Bluish, greenish.
Heading to green. Yeah. So that one is basic.
Basic.
Gotcha.
Now
Right.
we have a little bit of hydrochloric acid. Move that right. Tiny little bit of hydrochloric acid.
That sounds scary.
Whoa. That one is super pink. It's even redder than our vinegar over here.
Wow.
Next, we have hand sanitizer. Any guesses for hand sanitizer, Matt?
Uh-oh.
Dad? Do you think this is going to be acidic
No.
or
I think
basic?
oh wait, it kills the germs. It's probably because of acid, so it's going to be acidic, right?
Let's find out if you're right. Ooh, a lovely purple. So it's kind of more on the neutral side of things.
Or yeah. Okay. So it didn't change much at all.
Didn't change very much.
Okay. So if there's no change to the
I'm going to move
Color.
our hydrochloric over here so things are somewhat in order. And let's put our hand sanitizer over here.
okay,
Okay.
So somewhere near the middle of our rainbow of
Next,
pH.
this one, I had a little cotton ball on the top because this is ammonia, which people often use to clean with, and it's kind of stinky.
She's gonna make a mess. I know she's gonna make a mess.
I'm not going to make a mess, Matt. Don't
Oh.
worry. And then we're going to put
And-
the cotton ball back on top because that stuff stinks.
Oh my goodness! But look,
Whoa, really
look
green.
how green that is. That's like a dark green.
That's super dark green.
Forest green.
Next, we have bleach. So this is the bleach, like Clorox bleach that people clean with.
Okay. Ooh, is it gonna be acidic or basic? I don't even know. Oh, I do now. I mean, I knew it was gonna be a basic.
Now you know.
Yeah.
Now you know it's a base.
Um,
And this one looks to be not quite as strong as our ammonia. So I'm going to switch those around.
I agree. That's the right.
And last but
Grading
not
them.
least, we have some drain cleaner. Tiny bit of drain cleaner in here.
Little tiny vial here.
Whoa, that's very green.
That thing's
Interesting.
almost headed to yellow.
It
How,
is.
that's
It
how,
is
That's
almost
how green
yellow.
that is.
Now, let me kind of scoot these back just a little bit because I feel like there's a shadow so that you're not quite able to see the color change there. Look how that one's almost yellow. Then we have a dark green, and then we're getting closer to turquoise, and then to our neutral purple. We have a whole rainbow of colors.
This is crazy. Purple cabbage somehow can make all those colors. Is it hitting?
It's because of a special molecule in purple cabbage called anthocyanin. So anthocyanin is what gives this purple cabbage its color. And it's a molecule that is made mostly of carbon, oxygens, hydrogens, but it has a really cool property where it will change color when the pH changes. And let's do one last test. We are going to do water. So here is a cup of water. Let's go back to a big view, Math Dad, real fast.
Okay.
So this right here, I'm going to have you hold this for me for just a minute. This is just water and cabbage juice. That's
Okay.
all. But this was made with distilled water. And this is tap water that I got just from our tap. And now I'm going to add some of that cabbage juice to our tap water. And I'm curious, will we see a difference in color?
Wait, you're saying our tap water could be acidic?
Not much, but a little bit of a difference. It should look a little bit more blue. What do you think? Let's put them both in front of your shirt
Okay.
so that we have the same background. Does it look just a little bit more
I
blue?
think it looks a little darker.
I think it
little-
does. It's hard to
Yeah.
tell because I diluted it quite a bit. But our tap water is actually a little bit basic, just a
Oh.
tiny bit, because we have hard water That means that we have a lot of magnesium and calcium dissolved in our water. So sometimes at the store, I actually see these containers of water and they're twice as expensive as the other water. And they say alkaline water. And it always makes me laugh because I say, well, if you live in Nevada, your water is already alkaline. And so you don't need to pay twice as much money. You can just drink tap water to get that alkaline water.
So wait. Other places, though, it could be acidic?
At other places, if your water is soft, it's not going to be as basic. It's going to be more neutral.
Gotcha.
Yeah. Let's go to the notes real quick.
We
need to explain pH more. You've got questions.
I've got so many questions here, but you want to go to the notes and come back?
Well, let's do one more review of our colorful rainbow, and then we'll go to the notes and explain what pH is.
Okay. So we've got this whole rainbow of colors. Let me see if I remember this. This side was the acids.
Mm-hmm.
This side here, the more basic ones.
Bases.
And do they just... Are they the opposites of each other? Like they just cancel each other out if you pour them together?
So here's what's happening. On this side, the basic side, we have more hydroxide ions. Gotcha. There are more of these than there are hydrogen ions. Okay. And over here on the acidic side, we have a lot of extra hydrogen ions. And then in the middle, they're equal. We have equal amounts. So more hydroxide, more hydrogen ions. That's basically what the pH scale is. And at either end of the extremes, they can be dangerous. Math Dad, would you want to take a bath in hydrochloric acid?
Nope. No, I would not.
Let me ask you another question. Do you have any hydrochloric acid with you right now?
No. I don't like I keep it in my pocket or anything.
Well, you kind of do, actually. You keep it in your stomach.
Stomach acid is hydrochloric acid?
Yes. Your stomach acid is hydrochloric acid, which is very good for you because it helps you digest your food. It is not so good for the apple or whatever else you ate because it starts to break it apart because it's a strong acid. So anything you eat starts to get broken apart by hydrochloric acid. What about taking a bath in drain cleaner or ammonia or Clorox bleach? Would that be a good idea?
I'm guessing that's not a good idea.
No, not at all. And it's because these hydroxide ions, they're reactive too. And if you have too much of either one, that spells danger.
But it would get me nice and clean to bathe in cleaning products.
No. Nope. It's
bad idea all around.
Very bad idea.
But which one's more dangerous though? The acids or the bases?
It all depends on how concentrated it is.
Oh.
Both of them, when they're very concentrated, can be very dangerous.
So like burn you and all the damage that would come with.
Yes. And in fact, we have a special symbol. Let me show real fast. We have a special symbol for both strong acids and strong bases. And this is what it looks like.
Oh.
If something is a super strong acid or a super strong base, we say it's corrosive. And that means it could dissolve metals. It can do a lot of damage. So whether it's a super strong acid or a super strong base, both of them are things you need to be very, very careful with.
Did you say that acids could eat through metals?
Yes. Certain strong acids and strong bases can even dissolve metals. So you couldn't put them in a metal container. It would just drip out the bottom.
Wait, what type of container can you put them in?
There are Teflon, like the Teflon pans that you cook with. There are certain acids that are so corrosive, they can only be stored in Teflon containers, like a nonstick pan. So you have to have a special coating over the metal to make sure it doesn't dissolve. But the reason that they're so corrosive is because of their chemistry, because they are so good at causing chemical reactions to happen. And that's all because of, where'd my little hydrogen go? Here it is. And that's really all because of this, because when you have a lot of ions, and those ions are like, I'm positive I really, really need an electron. Or if you have a lot of these type of ions that have extra electrons and they're like, oh, I just wish I could give someone these electrons. Either one of these can be super reactive.
Gotcha.
Let's go to the notes real quick and take a look at the notes.
All right. Heading. Oh, I've got my.
That's Math Dad's math notes.
Indeed. Let's jump to the chemistry notes. All right. We are on page 44 in the printed notes, or 49 if you've got it pulled up on a computer.
Now,
all right. Acids and bases.
Now, Amna just asked a great question. Is this why drain cleaner is dangerous? Because you know if you have ever looked at the warning label on drain cleaner and some, toilet bowl cleaner and things like that, you know that these are pretty dangerous. And if they had a pH of 7, would they be safe? And the answer is yes. But then they would no longer clean your toilet or your drain.
Oh, so the dangerous part of them is actually what makes them useful.
Yes. Yeah, when you need drain cleaner to open up a pipe, it's because there are water deposits and minerals that have crusted in and clogged up that pipe. And hair and other things, a whole bunch of gunk has made it so water can't flow through. And if you put drain cleaner down the pipe, then because it's such a strong base, all those hydroxide ions, they're like, aha, here, the hair can have the electrons, the scum can have the electrons, and they start all these chemical reactions that open up the pipe. But if they had a pH of 7 and you put it down the pipe, it would just run through. It wouldn't cause chemical reactions.
So that they're actually useful, not just dangerous.
Yes, they have their uses. Strong acids and strong bases can be very useful, but we need to be careful with them because look where we are. So pure water is a pH of 7. Our blood, the inside of your body, has a pH of about 7.4. And salt water, like if you go swimming in the ocean, that's a pH of 8.
Okay.
So we really, this amount right here, this is kind of the safe zone. And if you get too far above or too far below, that can be dangerous, except for the special location of our stomach. Our stomach has a nice pH that is pretty similar to lemon juice, actually, right around 2. And that really helps us to digest our food.
I'm surprised to see that lemon juice is so acidic. So you wouldn't want to bathe in lemon juice.
No, if you took a bath in lemon juice, your skin would get wrinkly really fast and it would start to turn kind of white. And, after probably about a minute, it would start to hurt too.
Wow.
And as long as you rinse it off, you would be fine. But you don't want to take a bath in lemon juice or vinegar. No. You can actually bleach your hair by soaking it in vinegar or lemon juice. If you soak it for long enough, it will change the color slightly. It's not going to be as strong of a bleach as actually using bleach, but it can change the color of your hair.
I tried that as a kid. We put some lemon juice in my hair, and then went outside and played in the sun. I think the sun helped.
Really?
That's what I thought.
You tried to bleach your hair when you were a kid?
Oh, totally. Yeah.
With lemon juice, did it work?
Yeah. It was a lot lighter. It wasn't like white bleach, but yeah. This is my grandma's trick for making your hair look more blonde.
Interesting.
Yeah.
All right, let's look at this pH scale in just a little bit more detail because this is pretty cool.
All right.
So pure water, pH of 7, and that means the hydrogen ions equals how many hydroxide ions you have. So you've got equal amounts of those. But if we get more hydrogen, I'm going to grab the pen right here real quick, and I'm just going to write more hydrogen ions, then we are acidic. But the pH scale does not increase where, we have 5 is where coffee is, and then vinegar is just twice as acidic as coffee. No. It's a logarithmic scale. Math guy, can you say what that means? What does it mean if it's a logarithmic scale?
Ooh, logarithms are this tool that mathematicians use to work with exponents of numbers, which are still things that many of you wouldn't have heard of yet. So let's do an example here. So each step on the scale represents 10 times the concentration of the previous step.
Oh, wow. Is that the same way that the earthquake scale works?
That's right. So the Richter scale. So maybe you've heard of the Richter scale with earthquakes. Like a 6.0 magnitude earthquake is pretty sizable. And a 7.0, you might think, oh, well, from 6 to 7, that's just a step of size 1. But actually, it's 10 times bigger to go from a 6.0 Richter scale earthquake to a 7.0. And the same thing is happening here.
So if a 6.0 earthquake hit here, and then at the next town, a 7.0 earthquake hit,
theirs would be 10
times more powerful.
Yeah. Wow. Yeah. Okay, so we got the same thing here. So let's do an example. We have maybe lemon juice here at a 2.
Mm-hmm.
And over here, actually, soda's a little beyond that. But suppose we went from a 2 to a 4. So how much did the concentration go up?
So 3 would be 10 times more. So if we go to 4, is that 20 times more?
No, it's 10 times 10 times
Oh,
more.
wow.
So that means 100 times more concentrated.
So your stomach acid, the acid in your stomach is 100 times more concentrated than most sodas.
That's right, assuming they were right at 4. Yeah.
And soda, like soda pop that you drink, so it is slightly acidic, but it all depends on the brand of soda. Some are almost as acidic as vinegar. Others are kind of mild. It just depends. Yeah, a lot of these things can have kind of a range.
All right, let's try one more example here real quick. All right, suppose we went from this pure water up to window cleaner.
Ooh.
So
how
in that
much
case,
more basic would the window cleaner be?
Yeah. What's the change in the concentration? By what factor?
All right, I can do this.
Right.
So we're going to go 10 times more, 100 times more, 1,000 times more.
1,000 times the concentration.
Whoa. And so that means that liquid drain cleaner is way more dangerous than window cleaner because it is 10, 100, 1,000.
10,000 times more concentrated than window cleaner. So even though those steps look like small steps, the scale is off. It's a logarithmic scale. And yeah, that means that the gaps between those numbers are different than the one unit that it looks like, and that they're not all equally spaced the way that they're drawn here.
Now, we had a great question about why would there be more hydrogen if it's all just coming from water splitting apart, but that's not where it's coming from. I'm so glad that was asked.
Oh, that was a good question.
Yeah, because pure water, this is where the hydrogen ions and the hydroxide ions in pure water come from, and there are not very many of them. But hydrochloric acid, this most concentrated, the reddest one on our little scale there, it is made of HCl, hydrogen bonded with chlorine. And when you put that in water, it's like 100% hydrogen ions because all of the H and the Cl, they all separate. And so this is why it's such a strong acid. And then sodium hydroxide drain cleaner, it is Na, sodium, and then OH. So when you put it in water, you have almost like 100% hydroxide ions, but they're not coming from the water. They're coming from the chemical. So that was a really good question. Thanks for asking that.
Okay, that makes sense.
And then what happens if you mix acids and bases? Well, it all depends. It all depends.
So I do see a question here in the chat from Kendra, a fellow mathematician, is asking, is it base 10 logarithm? And yeah, actually my understanding is it is actually base 10 logarithm. Although kind of a fun fact, all logarithms are just scaled multiples of each other. So sometimes they'll throw a constant in there, but I actually think they use base 10 for both Richter scale and for pH.
And for the pH. Oh, I just made our, can you bring it back?
Oh, she did it. I saw, everyone witnessed. Science Mom did it.
That was my bad.
Right.
So I want to talk just real quick about not mixing chemicals, because this is pretty important, and what happens if you mix an acid with a base. And then we'll come back to the notes. So let's go to this main view up here real quick. Right. I'm going to put my gloves on again and safety goggles on.
No, try that again.
So vinegar, which is right here, this one here, is acidic. And then we had baking soda right here, which is basic. And what would happen if we mixed these two together? And I'm going to dump out my pure water right here so that I have my tap water, so I have just a blank container right here.
Ooh.
And
is this safe to mix?
Baking soda and vinegar are, but those are the only two that we're going to mix here. I just knocked the hand sanitizer off the table. It's okay. Those are the only two containers we're going to mix here because the other ingredients would not be safe to mix. So if we put a little bit of baking soda here, what's going to happen to the color when we add the vinegar? Math Dad, make a prediction. And if you are watching, I hope you'll make a prediction as well.
Just a sec. You're mixing the base and then acid, and the neutral color was that dark purple, like this, right? Okay. Yep. So my guess is it'll just turn purple again.
Let's find out.
Yeah.
Kind of swirl it around.
Chat's also guessing that it might explode.
It did turn purple.
Oh. Yep.
Because the baking soda and the vinegar reacted, and the hydrogen and the hydroxide were used up, and we don't have as much. We got back to neutral. Yeah. So that's kind of cool.
So it's actually forming water.
Yeah.
Is that right?
Now, anytime you have an acid and a base and you put them together, they are going to react, but we need to be very careful about combining chemicals, because if you combine two chemicals and they make something dangerous, then that is not safe. When we combine vinegar and baking soda, you know from previous experiments we've done, we're going to make a little bit of carbon dioxide gas. We're going to make some sodium acetate. We make things that are pretty safe. But if you combine bleach and ammonia, do you think you make something safe or something dangerous if you put these two chemicals together?
I gotta say, from the way you phrased that question,
Dun, dun, dun.
yeah, I'm almost hearing the ominous music in the background. Is dangerous?
Very dangerous. Every single year, poison control reports that there are poisonings from people who mix ammonia and chloride. And they mix them because they think, well, this is a cleaner. This is also a cleaner. If I mix this cleaner plus this cleaner,
That's super cleaner.
it'll be even more clean. But that is not true. You actually make a poisonous gas.
Ooh.
So never mix two cleaners together. That's something that is very important to know. And anytime I do anything that involves these cleaning chemicals, I make a point of saying that, because too many people get sick or even die from mixing cleaning products each year, and it should not happen.
So I gotta say as well, when it comes time for us to clean up afterwards, sometimes I'll just bring in a big pot and I'll dump all of Science Mom's experiments in there. I'm not doing that today.
Nope.
No,
Nope.
so
We take care of each of these individually.
So I always ask before doing it.
Now, back to how did the cabbage do this? I want to answer this real quick before we fill out our notes. So cabbage is kind of a cool vegetable because it has anthocyanin in it, which gives it this purple color. But did you know that we could do the same thing with blueberries, blackberries, purple cauliflower?
What?
Pretty much any food that looks purple is going to have this same chemical. It's called anthocyanin, and it's just a big chain of carbons, oxygens, and hydrogens, but they're all arranged into a shape where if the pH changes, their color changes. And you can see they have this beautiful, beautiful purple color. And if we were to dip this in just the piece of cabbage into vinegar, it's going to turn more pink. If we put it into baking soda, it's actually going to turn more green. You can change the color of your cabbage. If you're eating purple cabbage, you can change the color just by adding vinegar or baking soda.
Huh.
Pretty amazing, right?
Gotta say, that's kind of magical.
Yeah. Cabbage is my favorite for this, both because it's a little cheaper and because it just makes a large quantity of the juice. But it works almost exactly the same with blackberries, blueberries, or purple cauliflower.
And you could just drink that cabbage juice?
Yeah. Yep, the cabbage juice, as long as you haven't added any other things to it, is perfectly safe to eat. And then you have boiled cabbage that you can add salt to and season and cook up, and you can eat your cabbage as well.
All right, so if they want to do this at home, what recommendations do you have? What can they do at home?
I would recommend stick to just the vinegar and the baking soda, because you can, unless you have permission from a grown-up to test other things, and if you do test other things, don't mix them. These you can mix, and it is really quite satisfying to see the color change as you mix and add different things.
If they have like a lemon, get the grown-ups permission.
Yes.
Yeah, try this out. All right.
Check out this one. I'm gonna hold it just a little bit closer. I mean, look at just the variety of colors that you get. Isn't that pretty?
Whoa.
And if you mix them on a plate, then you can see like how the water current moves. Like if you pour just a little bit of one into the other, the way they interact and the way the colors move is really cool. All right, let's go back to the notes real quick, and we will finish out our notes. I did see someone ask, how do you juice the cabbages? You just take this piece of cabbage and put it in a pot of hot water and boil it. And you don't need to boil it for very long. I would say just a couple minutes. Elizabeth wants to know where the marmoset is on the acidic scale. I think this is a fabulous question, Matthew.
You know, you make one mistake and they never let you forget it. That's how this works. All right. I'm not relinquishing the pencil science, Mom. I'm going to do this.
You be the scribe.
All right. pH stands for, what does pH stand for? Potential of pH. I better start with H, right? And the only answer there is hydrogen.
That is right. pH stands for potential of hydrogen. And I want to tell you really quick, the thing I love best about anthocyanin and other pH indicators is that they're reusable. If we take this is purplish now because we added more baking soda. Can you open that vinegar for me real quick?
Yeah.
If we add more vinegar, we can change it back to pink. Watch this.
What? Oh, man.
all the way
And
back
if you
to
added more
pink.
baking soda, it would turn.
We can turn it back to blue.
And then could you turn it all the way to greenish by adding even more baking soda?
Baking soda is not going to get more than just the blue color because
Oh,
it's not a super strong base. But you can go back and forth indefinitely. You could just keep going and going, which is really kind of cool.
That's right. We got to remember to switch camera when you show.
Oh, sorry about that.
All right. Okay. pH scale is used to measure how blank or basic a solution is. I know this one. It's got to be acidic.
Acidic. Yes. How acidic or basic a solution is.
Okay. At room temperature, blank blank is neutral with a pH of 7.
So what has a pH of 7? There really is only one thing that has a pH of 7. One thing that we commonly interact with. Pure water.
Pure water. Thank you, chat. All right.
Pure water.
Pure water is neutral with a pH of 7. Okay. At neutral pH, the amount of hydrogen ions equals the number of hydroxide ions. Okay. And in an acidic solution, there are more blank ions than hydroxide ions. So
hydrogen.
More hydrogen, so more of the H plus.
More of the H plus.
But in a basic solution?
Yes, in a basic solution or alkaline. You'll probably see people talk about alkaline just as often as you'll see it called basic. There are two words that mean the same thing. We have more hydroxide. That's our OH minus.
Gotcha. Okay, that makes a lot of sense. I've heard of alkaline soils. Like I heard that you can only grow strawberries if it's
blueberries. Blueberries need an acidic soil, and other trees and will grow, and plants will grow better in an alkaline soil. But alkaline is really just caused by a lot of ions. There's magnesium and calcium in the soil, and that puts the pH more around right here instead of being neutral or even a little bit more acidic. And so we live in Nevada. Our soil and our water are both much more on this alkaline side of things. And that means if we wanted to grow blueberries, we would have to put them in a pot. We can't put them in the ground. They're not going to grow on the ground. So it's too hot for blueberries here.
That is true.
Sad emoji. All right, let's go back to a big view real quick. I want to do our chem mystery and make sure that we have time for our poll questions. So if I could ask one of our moderators to put that link in the chat for polls, we will have our chem mystery now.
All right. Gonna be a tough one today, Science Mom?
I don't think it's too tough. It's a good one.
All right.
This transition metal can be extremely destructive.
It's radioactive, but not very conductive.
It fuels nuclear reactors, and in darkness it glows.
Its bombs helped to bring World War II to a close.
What element is this?
Oh, boy.
What element?
I wouldn't be surprised if there was even more than one possible answer to this.
Rachel suggests uranium, and that is a great suggestion, and that does almost fit, but we're looking for one that has a slightly higher atomic number. And I'll give you a hint. The atomic number is 94.
Well, that's a big hint.
That is a big hint. It is not a noble gas.
Not that I have the table memorized, so I don't know what it is, but if somebody has their table nearby.
Yep, it's not uranium. Uranium's a good guess, though, because that was used with nuclear production, both for nuclear power and nuclear weapons. But there's another element that was also used. And it is atomic number 94. So
it's not a noble gas.
Mitch and Wares has it, plutonium. And Kai has it, plutonium. Hexa Harper has it, plutonium. Good job, you guys. That is correct.
Gotcha.
So plutonium is a very dangerous element, one that you would not want to handle because it is radioactive. 94 protons in the nucleus of plutonium. It is a big, heavy element. It's solid and silver in its pure state, but it's so reactive that it's what we call pyrophoritic, I think. It will react with air and start to combust spontaneously if you have pure plutonium. So that's why this sample here, you can see the sample in the jar is in a sealed jar surrounded by a liquid, some sort of like non-reactive liquid. So that, because if it's in air, it's going to react.
So Yvonne here has an explosion on the plutonium card.
Very Great job with the plutonium card. And I want to give just a special plug. So we sent out an email. If you are working on your elemental trading cards, you can earn this science notebook and some stickers. We sent out an email and we're seeing some fabulous cards being made. Great job, Charlotte and Ethan, on these cards for helium and gold. And I hope you guys will continue working on those. Now we're ready for our polls.
All right. I'm gonna throw this link in the chat. So head over to itempool.com/sciencemom/live, and we will try some poll questions. We'll see if I can stump them today, Science
I don't
Mom.
think you're gonna stump them.
I don't know. I know there are some easy questions, but some that are not so easy here. All right. We are indeed showing the correct piece.
Don't worry. It wasn't anything that had liquid in it.
All right. Our first question, Science Mom. What does pH stand for?
This is one of the most common questions that people ask when they learn about the pH scale.
Is it potential of hydrogen, perfect hydroxide, perennial helium, power of hydride? Is it penguins and hogs?
Or perfectly happy marmosets?
Oh.
I'll answer a couple questions while we have results coming in. So if you have questions, put them in the chat. Our moderators will text them to me. Can you store acid in a glass? Most acids can be stored in glass, but the most powerful acid on record, I looked it up and it's like hydrofluora something. It actually has to be stored in a Teflon container. It can't be stored in glass. It will even dissolve glass. But most acids, hydrochloric acid and others, can be stored in glass just fine.
Oh, that's pretty cool. All right, I'm going to finish and reveal here. It looks like 104 people picked potential of hydrogen, and yes.
Nicely done. That is correct. Also, sometimes power of hydrogen, they were both used synonymously when the pH scale was invented. And it was invented because you had people brewing different beverages who wanted to be able to describe what they tasted like, and just saying sour was not acceptable. They said, we need to quantify this. And that's how the pH scale was invented, actually.
All right. So which of the following is an acid? Out of vinegar, window cleaner, ammonia, lemon juice. Yeah, which
of those are acid?
So pH, if you tried to sound it out as a word, it's pH sound in English, we use like. So
English has the most bizarre spelling ever. Yeah. Yes.
All right. 2
of these we tested and they turned green, which is a hint that they are not acids. So there's my hint I'm giving you.
Okay. So this one's not as clear cut, although I do see 2 categories getting more votes than the others. Yeah. Tricky questions here. So yeah, could be any number of them here. The votes are still coming in. I think I'm going to reveal. And remember, if you don't get a chance to vote, make sure you're just voting in your head. All right. And they said vinegar and lemon juice are acidic. Are they right?
Definitely are. Yep. 100%.
Well done. Okay. I didn't stump them yet.
And vinegar and lemon juice are good examples that not all acids are dangerous, because vinegar is this concentration of vinegar, 3%, is really pretty mild. I mean, you eat stuff like this all the time when you make salad dressing and other foods.
Well, wait, is the 3% vinegar at that level of acidic, or
the 3% is important? So this is 3% vinegar, 97% water. If you actually have 100% vinegar, it is a much more powerful acid, and you don't want to put that on your salad. It would dissolve your salad.
Yeah. What about lemon juice? Is that the typical form of lemon juice when they say it's a 2.5 or so? Yeah.
Yeah, lemon juice is also, down to 2. We can interact with that pretty well. Our skin protects us, but you wouldn't want to take a bath in lemon juice. And if you suck on lemons or drink lemon juice too much, you'll actually dissolve the enamel on your teeth.
Oh,
so
that would be bad.
Yep. So if you're eating a raw lemon and just chewing on it or sucking on it, if you really like sour things, afterwards, rinse out your mouth.
All right, I started question number 3 already, but when we were talking, but so if you saw 3 hot spring pools that had signs displaying their pH levels, which one would be safe to swim in? A pool with a pH of 2, pool with a pH of 8, or a pool with a pH of 14? So one of those, and only one of those, would be safe to swim in. Which one is it? And I don't think when you go to a hot spring that it typically labels the pH, does it?
Some places do. So there is hot spring that's a commercial hot spring where they have natural, the water that comes through these vents, and then they've put it into swimming pools and things up in Idaho. And they actually do tell you as you're walking into the building what the pH is and what the mineral content is of the springs. And in Yellowstone National Park, there are signs by several of the pools that tell you what the pH is. But yeah, typically, no. Let's go ahead and finish and reveal.
All right. And B, oh, yeah.
Good job. Yeah,
got it
8
right.
would be like swimming in the ocean water. 2 would, you might be able to get in for a little while, but then you would want to get out and your skin would hurt. 14 would be terrible. That would be deadly hot spring. Don't get in a pH 14 hot spring. Next one.
All right. Question number 4. What is the pH of pure water? Ooh, this is not multiple choice. They get to enter a number.
Ooh.
Let's see if they can come up with the right answer here.
And good question here about plutonium. Is plutonium a transition metal? So plutonium, in fact, we'll after we finish our polls, we'll bring up our periodic table and show you plutonium. It's down on that bottom level, the actinides, lanthanides part. And those are typically grouped in with the transition metals. Most of the periodic table is transition metals. So that was a good question.
All right. We're getting a lot of different answers here, but most of them are picking just one value. I don't think I've stumped them this time.
I don't think so. I think they're going to get it.
Okay.
We also had a good question about dry ice, because if you put dry ice in cabbage juice, it will change the color slightly and it will get just a little bit more acidic. It will turn a little bit purple. And could you drink that water that has dry ice in it? Well, if the dry ice is still in there, I'd say don't drink it. Wait till the dry ice all sublimates. But once the dry ice has all turned into a gas, yes, you could drink it. And that's essentially what soda is. Soda, when you drink a carbonated beverage, it has carbon dioxide gas in it.
Cool.
Let's finish and reveal.
All right. The correct answer is pH of 7.
Nicely done.
Cool. So several answers there were goofing off, but yeah, almost everybody got it. pH of 7. Okay.
Next one.
Pretty smart crew here. All right. What happens if you combine an acid and a base? Do they react, or is there no reaction? They do not react.
Where did our little, oh, here they are.
Yeah, what happens?
If you combine an acid and a base, do they react or do they not react?
Oh man, I thought this one might fool some people, but maybe not.
No, I don't know. I don't think you fooled anyone this time, Matt.
Oh.
You'll have to try harder.
One of these times I'll get you guys.
It's a good thing to remember that although the best way to explain the pH scale is hydrogens and oxygens, what we really care about is things that want electrons and things that want to give electrons. That's what really matters, because it's possible to have an acid without having a lot of hydrogen ions, but just having other things that really want electrons.
The answer is they react.
They do.
Big time reaction.
Because an acid is something that is going to want to get electrons. A base is something that has extra electrons to give. And if you put something with extra electrons in with another thing that really wants those electrons, they will react. You will definitely have a reaction.
It makes a lot of sense. And something interesting here, you called this an ion, right, Science Mom?
Mm-hmm.
So an ion doesn't necessarily just have to be a single atom.
Ooh,
it can be a
compound. Yes, a compound can be ionic. That's a good thing to point out, Math Dad. Absolutely right.
The smallest particle of all is one called the electron. Take away or add it in, that's how you get an ion.
And a lot of times when we talk about ions, they're just a single atom, but sometimes they can be a compound. And the hydroxide is an excellent example of those. All right, let's talk about plutonium super fast, because there were a couple good questions about plutonium that I wanted to answer real quick.
All right.
So element 94 down here on the periodic table.
Very bottom.
Yes.
All right.
And go back to the periodic table real quick. I just wanted to point out, remember this section here.
Whoops.
Whoops.
They can't see where you're pointing, Science Mom.
Oh.
The bottom row, though?
These bottom two rows are usually, or where they should go number-wise is right in the middle of the chart. But remember how then that makes the chart super huge? On, I think, page 3 or 4 of the notes, we have the chart all drawn out. Here's how it looks if you just arrange it by number. So plutonium is a metal, but it's a metal that is extraordinarily dangerous. Another question was, could you eat plutonium? It would not be pleasant if you did. So if it was pure plutonium, first off, if it's pure plutonium, as soon as it comes into contact with oxygen, it's going to be on fire. And so you'd be eating something that would literally be like radiating dangerous radiation and be on fire itself. So no one should ever eat any of the radioactive elements. That is my firm opinion.
Those will not be on the cereal box anytime soon?
No.
All right.
No. All right. We are out of time, you guys, but thank you for joining us today. I hope you enjoyed this lesson. And tomorrow we have our next game show review. So we hope you'll be able to join us for a game show review. Math Dad might stump you then, because he did make some harder questions for tomorrow.
It's going to happen.
We'll find out. Take care, work hard, grow smart, and we'll see you tomorrow.